Assalamualaikum to fellow panel and lecturer. My name is Nur Fara Diniy binti Azizi. I'm a master student from Faculty of Mechanical Technology and Engineering. My metric number M132510009. Today I will be presenting my research proposal entitled A DOE-based investigation of electrospinning parameter on the morphology and contact angle of PVA nanofiber for air filtration application. This purpose study focused on systematically optimizing electrospinning parameter using a design of experiment DOE approach to better understand fiber morphology, wettability, and filtration performance. Electrospinning is a well-established technique for producing nanofiber with diameters in the nanometer range and very high surface area. These properties are particularly suitable for air filtration application, especially for capturing the particles such as particle matter 0.3. In this research, polyvinyl alcohol or PVA is selected because it is biodegradable, environmentally friendly, and can be processed using tap water instead of toxic organic solvent. However, electrospinning is extremely sensitive to processing parameters, and small change and significantly affect fiber quality. This motivates for the needs for systematic investigation. The morphology and performance of electrospun nanofiber are strongly influenced by several parameters, including solution concentration, applied voltage, tip to collector distance, and feed rate. Inappropriate combination of these parameters can lead to defects such as bead formation and non-uniform fibers. Additionally, PVA is inherently hydrophilic, which raises questions about its suitability for air filtration application, especially in humid environment. While many studies have examined individual parameters, most rely on trial and error methods. There is a clear research gap in systematically analyzing parameter interaction using a statistical design of experiment approach and link the result to filtration performance. This gap forms the basis of my proposed study. Based on identified research gap, this study is guided by two main objectives. First, to investigate the effect of electrospinning parameters on the average fiber diameter using DOE. Second, to study the surface wettability of PVA nanofibers through contact angle analysis and evaluate the influence of optimized parameter on air filtration performance. These objectives are supported by research questions that focus on understanding how individual and interacting parameters affect morphology, wettability, and filtration behavior. The scope of this research is clearly defined to ensure feasibility within the proposed timeline. 4 electrospinning parameters are selected as independent variables, while average fiber diameter and contact angle are measured as dependent responses. Environmental conditions such as temperature, humidity are controlled to minimize experimental variability. This controlled setup allows for reliable statistical analysis and meaningful interpretation of results. Air filtration is important, but we face a dilemma. Current high-performance filters often use toxic solvent or complex, multi-step processes. As seen in my comparative analysis, researchers like Chui et al. Have moved toward green PVA spinning, but their work lacks the statistical rigor needed for industrial optimization. My literature review position my work within existing research. For example, Liu create a super hydrophobic bilayer which is effective but complex. Moghadam used advanced RSM and ANN models, but on different polymer. My research aims to combine the strength of these studies, applying rigorous statistical DOE, like Moghadam and Tajan Langit did, to the environmentally friendly PVA system studied by Chui and Asuri, while also directly testing filtration performance to create a complete picture. By integrate Phase 5 quality factor analysis, I will prove that my research can create eco-friendly filters that are just as breathable and moisture stable as their toxic counterparts. We are moving from trial and error to precision engineered sustainability. Phase 1. Instead of trial and error, we are using design of experiment software to manage 19 specific runs. We are manipulating 4 critical variables: polymer concentration, 8 to 12 weight percent, distance 10 to 20 centimeter, voltage 10 to 20 kilovolt, and feed rate 1 to 2 milliliter per hour. To keep it sustainable, we use PVA dissolved in tap water mixed for 3 hours to ensure absolute homogeneity. Phase 2 is the electrospinning process. Using this ES1A electrospinning machine, we deposit fiber into an aluminium foil collector. Each run is strictly timed for 15 minutes to maintain consistency across all samples. Phase 3 is where we look at the results. We are scanning electron microscopy (SEM) to analyze the morphology and measure the average fiber diameter. Simultaneously, we perform contact angle testing using 5 microliter droplet and ImageJ software. This tells us exactly how water repellent our green membrane actually is. By the end of this minute, we have the data. The next minute is about the performance. In Phase 4, we conduct air filtration testing. Following the standard set by Zhou and colleagues, we challenge our optimized membranes with particulate matter 0.3 natrium chloride aerosol. Why 0.3 microns? Because it is the most penetrating particle size. If we catch this, we catch almost anything. We maintain a constant phase velocity of 5.3 centimeters per second to simulate a real-world breathing condition. Finally, in Phase 5, we perform data validation and corrective factor analysis. We don't just look for the smallest fiber, we look for the sweet spot. While fine fibers increase efficiency, they also increase the pressure drop, making it harder to breathe. We use the quality factor formula to mathematically balance capture efficiency against air resistance. For this research, I expect several key outcomes. First, a set of optimized electrospinning parameters for PVA nanofibers. Second, the ability to precisely control PVA nanofiber morphology for target applications. And third, an improved fundamental understanding of 3 things: the interaction between process parameter, wettability, behavior of PVA fiber, and a solid basis for future material modification. Ultimately, this work is about gaining control and predictability over the process. In conclusion, this proposed research presents a systematic and statistically driven approach to optimize electrospinning parameter for PVA nanofiber. By combining green processing, material characterization, and filtration performance evaluation, this study aims to contribute to sustainable air filtration research. Thank you very much, and Assalamualaikum.